All right, now you're ready for my perfectly imperfect Module 1 demonstration. I'm going to begin with some data that was from the Cohen and Cohen book from Chapter 3. It's a salary data set, and I read it in, and I'm all set to go. I'm going to run my bivariate and my multiple regression one after the other. And so what I've done here is I've read in the data set already, and what I want to show you is that I have two regressions. Now, before I get into too much of this, I want to explain what regression is about. Regression is a tool, a statistical tool, that allows us to model relationships between a predictor and an outcome, or a criterion, or multiple predictors and an outcome. And the reason for this is that when we're faced with a single variable and we're trying to expect what the outcome is, the best guess is the mean. And the mean oftentimes isn't very informative. So sometimes we can get a boost, a hint, and that hint is a predictor. So if we get a predictor like what your undergraduate GPA was, that might give us a hint as to how well you will be suited for graduate school. We assume that there's a positive relationship. The better you do as an undergrad, the better you will do as a graduate student. But sometimes that single predictor doesn't do very well alone, and we need lots of predictors, like whether you're conscientious, so we give you tests, and whether you have a good fund of knowledge, so we have more tests, and whether people like you, so we ask for letters of recommendation. And each one of these serves as a predictor that we can either use in a qualitative model, or in this case, we can use it in a quantitative model. In a quantitative model, if we gather a lot of data from all graduate applicants to find out if they're suitable for graduate school or not, we can create a prediction equation, and that prediction equation is in the form of regression. And regression has a long history, and it started out with Galton, and it moved on forward to refining all sorts of procedures, including what we've discussed so far. Regression is based upon ordinary least squares, and we're going to start looking at all the details. The ordinary least squares allows us to get our best linear unbiased estimate, provided our model meets all regression assumptions. So let's dig in now that we know a little bit of the purpose of regression. Regression is to describe and then eventually to predict. So I want to describe all of the previous applicants to our program, and then later I want to be able to predict whether somebody does well. So in this case, I'm looking at salary data and the amount of time on the job and number of publications and whether they're female and the number of citations. So my first model down here, I'm only looking at time, and as you can see, time is a positive predictor. The longer someone's in a job, the more money they're going to make. And the best way to look at this is just to show you what the plot looks like. And that's the plot. So the longer somebody is on the job, the greater their salary. And you can see that this red line is the line of best fit. And that line of best fit tells me that overall, there is a regression line that can be put through these dots, and then it has a positive slope. But I need to look into the numbers to be able to understand what the full regression line is. So first, we look at the intercept. The intercept is what would happen if somebody had 0 time, and that would be the Y value, and somebody would make, according to this, about $45,000. So $45,000 would be about here, right? That's, I think, is about 0, and that would be $45,000. That's the expected value with 0 time. And then, for every change, unit change in time, we expect about $1,380 increase in salary. So now, these are just the parameter estimates. So the bivariate regression equation would be salary equals 13,079, I'm just rounding, 13,079 times time plus 45,450. That's our bivariate regression model. Now, each one of these parameters has an associated standard error that we use to do hypothesis tests. And we have two separate hypothesis tests here. Where the first one is we want to know whether the intercept is significantly different from 0. That is, that when x equals 0, y equals 0 in the null. And as you can see here, the probability is vanishingly small, meaning it's below 0.05, and therefore we reject it. The probability of observing this data, given the null hypothesis, is very low. And it's not very significant, it's just significant at the 0.05 level. Okay, it's also significant at the 0.01 or the 0.001, something like that. But you get the picture. T-value is high. The way we get the t-value is we take the parameter estimate divided by the standard error, which is the lack of precision. And standard error is estimated by what amounts to be the standard error is a measure of precision, and it reflects how uncertain we would be about this parameter estimate here. And as we talked about in many of the lectures, that this standard error reflects the sampling variability, and so we would expect if this were a teeny tiny sample, the standard error would be increased, and later when we start adding predictors, standard error is affected by all sorts of things, in particular multicollinearity. So here we've got a bivariate model where time is a significant predictor because the p-value for time is, the p-value is sufficiently small enough, we reject the null, so this too is significantly different from 0. Then we move on to our multivariate model. Now I've thrown in a whole bunch of variables. We have our intercept and our time, number of publications, whether someone's female, and the citations. And so you'll see that, you'll notice that the y-intercept changes. It's no longer 45,000, it's about 39.5 or 39.6. Okay, it too is significant at the 0.05 level. Time is still a significant predictor. You notice the asterisk here, and there's a right here. It's at the 0.001 threshold, but you can see here it's 0.004. That's the probability. It's got a sufficiently high enough t-value, right? Because that's the parameter estimate divided by the standard error. These, by the way, are partial correlations, and they're partial correlations because they're each one of them is the part of the correlation between the predictor and the outcome, the criterion, with the other variables taken into consideration, or basically taken out. So it's the unique common variance shared over the total variance, both common and residual, that is an interpretable effect that we get when we're calculating any common variance in a regression model where you have multicollinearity. Now, I don't know whether there is much collinearity here, so I can check this from using this function. You'll see that time is fairly has a high VIF, and so does pubs. And the problem with time is still significant, but pubs is not. Pubs is not significant, and so therefore there is potential where multicollinearity has affected the standard error estimate, inflated the standard error estimate sufficiently to make pubs no longer a significant predictor. And what we can do is we can find out what the relationship is and which one is most collinear, probably time and pubs, because this probably go together. And if we use pubs alone as a predictor, and I can do that. Watch this. If I just do pubs, whoop, I'm going to run out of time here. And then I do this. And the reason why I'm doing this is I just want to see whether pubs is significant predictor. So let's just take a look at the bivariate plot. Bivariate plot, pubs, salary, that's looking pretty good. And let's just take a look at summary demo 3. Well, lo and behold, pubs is a significant predictor of salary alone, but because of multicollinearity, pubs goes away, because pubs and time are probably correlated. Let's just do a correlation here. Pubs and time correlated, 65. That's pretty high correlation. So there's potential for multicollinearity here. And if I really wanted to get down to it, what I would do is I would do a plot of all of the residual plots to take a look. These are diagnostic plots, and you can see that we've got a little bit of a problem with the distribution of our residuals, potentially leading to some problems of inference. And you'll also see that there are some influential values here that don't produce too much leverage overall, but there are some problems here, some problem observations that potentially skew our results. You'll notice that they're up here, for, observation 48, 32, and 55, and you can see here, there's 48, 32, and 55. See what happens is they push up our residuals a little bit, and here's 48 and 55. These are pretty big standardized residuals with not a whole lot of leverage. As soon as we get far out here, I start having problems. But overall, not bad. Not bad. So I think our bivariate model looks like it performs pretty well. Our multivariate model, however, has some problems, primarily because of multicollinearity. Overall, I would say I've got a nice uniform set of residuals. They're not great. They're mostly stacked up on the lower end, as you saw from the plot that I did right here. That when I did this plot and this plot, you'll take a look that most of my values are pretty far down here. Now notice I'm no longer using an x variable here. I'm using predicted y over to observed y, and the reason for it is you can't plot. Well, I could plot like a 3D surface, or in this case a 5 dimensions. Let's see, what is it? 1, 2, 3, 4, 5. Yeah, there'd be a lot of dimensions. But I don't even know how to read 2-dimension plots half the time, so I'm going to stick to predicted y to observe y, because this tells me what the relationship overall is, how well our prediction model's working, and it looks like it's predicting pretty well. And we can tell that by just looking at the summary of my demo 2. And it is working pretty well. I'm explaining about 50% of the variance. I round up. It's 47% if we take our adjusted r squared instead of just our multiple r squared. Overall, we're doing pretty well. Now, I ran through the diagnostics. I went through all of the results. And the implications are that, boy, if you're going to get a high salary, you just got to survive. Be in the job long enough, because if you're in the job here, let's go up here to our bivariate model. If you're in the job long enough, you'll get about $1,400 each year. As opposed to, if you look at other things, of course, you got to be in the job long enough to do pubs, to publish. But for each publication, you only get $350. So you're better off just surviving. And that's the implications of this model. Kind of a dire implications, I would say. Now I'm at 13 minutes, and now I'm at 14 minutes on my demonstration, and I haven't even gone through optional readings. Now I could have easily done this, and I wouldn't have had to go through the history and all of that, but I'm going to call it quits here. And the reason why I'm going to call it quits is I'm going to tell you that that was a perfectly imperfect. It was unrehearsed. I've never done this before, and in fact, I haven't even looked at this data before. I read it in prior, and I've copied and pasted it into my previous, I think, week 4 code, but I have not looked at these results, so this was all a clean, dry run. Is that a good thing? Well, it's okay. I'm the professor of the class, but at the same time, you guys will do much better than I will. Even though I know how to use R, you guys are facile with your own stats package. You'll have the data sets ahead of time. You'll know how to run these models. You'll know how to tell a story. You really have a much better understanding of what you're doing, and you'll feel comfortable. And here I'm up against the time clock. I've got a big clock right in front of me that tells me how much time. I'm at 15 minutes and 5 seconds right now. So I know exactly how much time I've been wasting on this. And remember, you only get 15 minutes. So what would I have done differently? Well, one, I would have practiced. By practicing, I would have eliminated a lot of the time where I had to go back and type in my demo 3. That was expensive in terms of time. I think I would have streamlined my description and my overall synopsis. I think some of the positive things I did is I did the bivariate and multivariate model one after the other. It's a lot easier to do it that way than to do the bivariate model and go through everything and then go through the multivariate model and go through everything. I just think that's inefficient with time. So for me, this worked. It worked okay. Probably I would have garnered a 1 from this from me. But you can do better, and I expect you to do better. So show me what you got. Perfectly Imperfect Module 1. Thanks for your time.